Thank you, Mr. Chairman. I'm Sudo from Tokyo Tokyo University. Today, I would like to talk about study on behavior of escalator during earthquake. In this presentation, we will talk about the following. First, I will explain the background and purpose of this study. Secondly, the vibration experiments will be described. Third, the seismic response analysis of an escalator is described. This analytical model was modeled using two different methods from escalator restoring force. Finally, I explain conclusion. This slide shows structure of escalator. As you know, escalator is one of the vertical transportation. For example, the escalator connected floor from other floor in buildings. In general, one side or both sides of escalator are not fixed to a beam or building, and non-fixed side is fixed at the time of an earthquake and can suppress the transportation of the escalator. However, in the Great East Japan earthquake in 2011, escalator body floor accident occurred. In these accidents, the escalator that connected the second floor to third floor dropped in the commercial facilities. This figure shows a falling escalator. After these accidents, the quake resistance standard was revised in Japan. According to this standard, the rear displacement of buildings to be expected during earthquake is more than before. The length of escalator hanging to beams of building is called overlap allowance, as shown in equation of the overlap allowance. Before the revision of quake resistance standard was less than 100 rad. After the revision of quake resistance standard was 140 rad in principle and 124 rad or more. However, escalators greatly shakes by a major earthquake and collide with beam of building. Moreover, the escalator may be damaged by compression and fall by losing the support capability. From the above-mentioned background, the purpose of this study is to grasp dynamic behavior of an escalator at earthquake with considered impact with the beam. In this paper, there are two purposes. First, in this experiment, to clarify the seismic behavior of the escalator including collision phenomena. Second, an analytical model is used to reproduce the behavior of the vibration experiments. Moreover, the restoring force characteristics of the escalator are modeled using two different methods to confirm the validity of the modeling method. This slide shows about vibration experiments. This specimen is composed of an escalator model and buildings model. The parameters of each model are listed in the table. This model is a 310 scale model of a 3-meter lift escalator. The specimen was set up as shown in the photograph. Vibration experiments are conducted under the condition of non-collision, collision, and backward. Their conditions are switched by changing the gap. This slide shows input weight. The input seismic waves, which are used in vibration experiments, are scaled by a similarly low with a constant velocity. Accordingly, the acceleration is 3.3 times the observed seismic wave, moreover 0.3 times the time. In this paper, scale of the JMA-NS original 0.25 meter per second and 0.5 meter per second seismic wave are used. These photos show the specimen before and after the vibration experiment. The buckling of the escalator occurred at the bottom. The bottom part of the escalator was confirmed to be sinking and deformed. This right is result of seismic experiments. We focus on the displacement that may affect the fall of the escalator. The figure shows from the top the displacement of the escalator, the displacement of the building, and the relative displacement of the escalator between buildings. In non-collision case, the maximum relative displacement is approximately 23 mm. The maximum relative displacement and the maximum building displacement are almost the same. The maximum escalator displacement is less than 1 mm, which is negligible in terms of relative displacement. Similarly, when a collision occurs, the relative displacement and the building displacement are almost the same. The displacement of the escalator is increasing, but it is negligible. In this case, the deformation has not reached yield displacement. However, when buckling occurs in the escalator, it cannot be ignored and affects the relative displacement. The restoring force characteristics are in the range of secondary stiffness, and the load is reduced after buckling occurs. The presence or absence of buckling was confirmed to be important in the evaluation of escalator force. This slide shows the analysis method. In this analysis, the escalator and the building are each one mass model. In order to reproduce the displacement after buckling, the restoring force of the escalator is modeled in two ways. In this analysis model, the collision is reproduced by the collision stiffness between the escalator model and the building model. In addition, we focused on the horizontal behavior of escalator truss, which is considered to be main cause of floor accident. This slide shows equation of motion analytical model of escalator. The motion equations are classified into two cases. One is the non-collision case, another is the collision case. The transition condition is equation 1. The parameters are the same as in the experiment. The restoring force of the escalator truss is modeled in two ways. One is a bilinear model. When the escalator displacement exceeds the yield displacement, the stiffness switches. Next is the differential equation model. The history loop can be created by determining the function of the skeleton curve during loading and unloading. The functions are determined from the restoring force characteristic obtained experimentally. The slide shows the result of the seismic response analysis of the linear model. For non-collision and collision, the maximum response value and the waveform torrent of the experiment can be reproduced. In the backwing case, the maximum building displacement is approximately 38 mm. The relative displacement of this analysis is slightly smaller than that of the experimental. However, the waveform trend can be reproduced. The restoring force of this analysis model reproduces the experimental trend, albeit in the simplified way. Accordingly, the behavior of the building and the escalator during earthquakes can be reproduced with ramp mass model. The behavior of the escalator after backwing can be reproduced with a linear model. The slide shows the result of the seismic response analysis of differential equation model. For non-collision and collision, the maximum response value and the waveform trend of the experiments can be reproduced. In the backwing case, the maximum building displacement is approximately 38 mm. The relative displacement of this analysis is slightly smaller than that of the experimental values, as in the linear model. However, the waveform trend can be reproduced. The restoring force of this analytical model reproduced the experiment trend. Accordingly, the behavior of the building and the escalator during earthquakes can be reproduced with a ramp mass model. The behavior of the escalator after backwing can be reproduced with a differential model. Moreover, there was no significant difference in this result between the two analysis models. In this study, the behavior of the backwing and the escalator during the earthquake was confirmed with the vibration experiment with the 3-10 scale model. The vibration experiment confirmed the following. The main cause of the fall of an escalator truss depends on displacement of the building. However, as the escalator backs, the backwing displacement factor increasing. The analysis confirms the following. The ramp mass model is effective to confirm the behavior of the building and the escalator during earthquake. In addition, a linear model and differential equation model is effective to reproducing the behavior of an escalator. This modeling method is used to grasp the behavior of the escalator during an earthquake and to evaluate the safety of the escalator. Thank you for your attention.